And then the seal was like
well, I was gonna go under it, but
Okay, let's get started here. So, we got an exam on Wednesday, you already know. So, a couple of things here that we should try to do here. I think I said that can we start at 9:20? Is there a problem?
I'll probably gonna be like 5 minutes later, so.
I'll give you that 5 minutes afterwards. Okay? And then I want to go till 10 minutes after, so that means that I want to shoot for 11 o'clock. So that gives you an extra 20 minutes from the exam. Okay? So we start at 9:20 and we go till 11 o'clock. Okay, remember, chapter 6 on ideal op-amp is not going to be on the exam. I'm going to set the problem set to be due on Wednesday after spring break. Okay? But I think what you'll see here is that you'll find out that it's fairly straightforward to actually do these things. Once you see the techniques that we're going to use, I think you'll find that they're very, very, very powerful. So let's go over the sort of like the model that we're going to be used. I said that this model is fairly complicated, but we're going to use this sort of a model to actually do that. And what it says here is that the input terminal currents are 0. So when I look at I1 and I2, anything along that branch is 0, anything along this branch is 0. And the other thing that it says here is that the node voltages at the input nodes are equal. So that means that that node relative to the ground, this node relative to the ground, we're going to treat as being the same. And one last thing that we should really say here is that you can't write V out as a node equation. Okay? You can't write those out. And the reason is remember, V out is the value, it's the voltage source. Right? It's the voltage source. And so what we're really seeing here is we're seeing this thing here. So when I look at this node right here, what I'm really seeing here is that I'm seeing this, is that 1 and 2 are the input, and then V out is the output. So it's essentially something like this. I have a circuit. I'm going to take V1 and V2 relative to that, and then all the way somewhere else in the circuit, I'm going to get V out that's equal to some scale factor versus V in. So if you try to write a node equation for V out, that doesn't make any sense, right? You can't write a voltage source as a node. You can write the node above and the node below, but you can't write that as a voltage node equation. So what we want to do then is that we want to start looking at the examples. Okay? So what I'll start here is that I'll start with some simple examples just to give you a sense of where we're at here. And the first circuit that I want to look at here is I want to look at a voltage follower. And what we know about a voltage follower here is that the gain is set to 1. Okay, so I'm setting the gain to 1. And what you're seeing here is that I have something like this here. So imagine that I have an op-amp that looks something like this. And this is some V source. This is some resistor. I have a load resistor. And then what I'm going to do here is that I take that feedback line and I attach it back to the input line like we did in lab. Right? This is the feedback line. So the first thing that I would do here is that immediately what I'm seeing here is that I look at the first condition and it says that the currents must be 0 on any branch. So when I look at this branch right here, right, that means the current flowing here is 0. So if that's 0, then that means that there's no drop across that resistor right there. So right away, the I equal to 1 equals to 0 implies that there is no voltage drop across R. So it's a dead resistor. So what you're seeing here is that this node, then V1 or V2 must be the exact same voltage drop across this. So then what we're seeing here is that if I come in, you're going to see that this node right here, V2, so then I look at that second condition here and it says that V2 must be equal to V source. Right? So the first condition is this one right here. The second condition is this one. And according to the ideal op-amp model, it immediately tells me that then it must be that. So when I go and I look at this node right here, that tells me that V1 must be VF. But wait a minute, here's a line, so as the line goes all the way across, you can now see that the drop across. So then this implies here that V out, which is the same as V2, must be the same as V source. So whatever voltage drop I put at the node 2, it automatically goes to the output voltage. Okay, so that's a fairly straightforward example of how I'm applying those two conditions. Let's look at another example about a non-inverting op-amp. So when I look at this guy here, what we're seeing here is that I'm going to draw this circuit in a way that that's not the common way that we look at here. So I'm going to put the positive up at the top instead of the negative. And then what you're going to see here is that I have a feedback resistor, which I call R. And then I'm going to call this resistor R1, which will be attached to the ground. And then if I have a feedback line, then that means I got to go from the negative down to this node right there. And this node right here I'll call V out. And then let's say that this guy is just some V source. So the first thing that I would like to do here is that note that I have the polarity that's positive and negative. So what I want to have here is very similar to this case. I want to draw it with the positive down and the negative up. I don't have to do that, but it's more common that we do that here. So what I'm going to do here is that I'm going to reverse the order. So if I reverse the order of the op-amp, what you're going to find here is that I'm going to, so now if I look at that, here's my op-amp. So I want the negative on top here, and the first thing that you see here is that this feedback resistor, if I look at this thing, if I just flip this whole thing upside down, what you're going to see here is that that feedback resistor has to come and attach to the output node. So this would be RF. And if you look at that resistor, this resistor is connected between these two resistors, so it has to come out so that this guy is doing what? And this guy's let's call that R1. And then you can see that this positive is attached right here, like this. Now I can make this a prettier circuit if you want. We don't have to do that. But I can connect, because note that that ground and that ground must be the same. So note, I could also have drawn this like this, and that would have been totally fine. And if you find this to be easier, then I suggest that you draw it that way. Right, that looks just exactly the same. Okay. I would have probably drawn it this way. So what I want to do here is that the first thing I want to do is that I'm going to do it two techniques. So I'm going to use two techniques to solve. So the first method that I want to do is I want to use simple circuit technique. So when I look at this guy here, I start to draw all of the currents here. Okay? So the first thing that you see here is that look at this line, look at this line. Do you see any resistors along these lines? The answer is no. So what I do here is that I'm going to apply ideal model immediately. And what you see here is that I1 equals to I2 equal to 0 gives us nothing. Right? It doesn't give us anything. So if I draw that again, just look at this here. So if I look at this guy is current I1. That's equal to 0. This current here is I2. That's equal to 0. So then the next thing that I'm going to do is I'm going to look at the next condition. The next condition implies that V1 has to be equal to V2. So now let's look at this here. So what I'm going to look at here is I'm going to look at nodes. So if you look at the node, note that this node up here is V1. This node right here is V2. So right away, what you're seeing here is that node V2, since there's no resistor there, is that voltage source. So that voltage source now comes right up to here. Okay? So now what I'm seeing here is that this implies here that V1 is equal to V source, which is now equal to V2. So I immediately get what the node V2 is here. Now, follow the current. If you follow the current, note that in the circuit here, if there's no current in this branch, then there has to be going a current of R1 down that direction. Right? So that means here that the current must be going like that. Now, let's give this value, let's give something, a numerical value to this current. How about if we call this Ix? So Ix goes this way, but note, R1 and RF are in series because there's no current going there. So then that means, I should be careful when I say in series. What I mean series is that they share the same current. So Ix is also the current there. So now, you can also see that the current in the op-amp must be like this, because this is open, so there's no current there. So you can see that the current Ix goes all the way around. So, here I go. So what I want to do now is that the goal here is to solve for V out. So if I solve for V out, I really need to learn the current. So what am I going to do? I'm going to apply Ohm's law now. So I'm going to solve for V out by applying two Ohm's laws. Okay? So here we go. So I know that if I look at just the resistor R1, so if I look for R1, this tells me here that V1 must be R1IX, right? That's the ground. Maybe I should put a 0 here, just to remind you that I'm talking about the ground. So this implies then that IX must be V1 over R1. Okay? So now I'm going to look at resistor RF. Okay, I looked at R1, here's RF, and when you look at this, the current here is the same as the current there, so then if you look at this, you go V out minus V1 must be what? The current through RF, so then this has to be RF times IX. They're the same. But what's IX in this case? IX must be what? It has to be RF times IX will then be V1 over R1. So what am I going to do? I'm going to do this here, so now I'm going to solve for V out. So if I look at V out will then be V1 plus RF, R1, V1, or 1 plus RF, R1 times V1. And I get that current. Let's see if we could just step back a moment. So what you're seeing here is that I'm not really doing complicated calculations, if I could say that. But somebody walking by the room would say, like, what are you talking about? That looks really complicated. But it's not complicated. Just check it out. All I did is I applied the ideal conditions right away to the circuit. Okay? That being the case here, I'm going to solve I out by using two Ohm's laws. So I applied Ohm's law at R1, right? V1 gives me this IX. And then I applied Ohm's law to this one here. So now I spent a fair amount of time writing this out, but with a little bit of practice, I bet you could just go almost, right? A little bit slower than that, but almost that fast. So these simple circuit techniques that we're using here are always sort of like far superior in general. So let me show you the other technique, node analysis. So if I apply node analysis to this thing here, what I got to do here is that I do it the following way. So now, method 2 here is applying node analysis. So when I apply node analysis here, I'm going to redraw my circuit here just to make sure that we're nice and clear here. So if I look at this thing here, the first thing that I'm going to do here is I'm going to look for nodes. So this node I already know because that node is at V1. Maybe I should call this VS to separate it. And then my other node is this node right here. Now the question is, can I write this as a node equation? And the answer is no, because this represents the voltage source. So you, like I said before, cannot write a node equation for a voltage source. What we do write is we write node equations for the nodes around the voltage source. Okay? So when you're seeing this here, if I look at the nodes, look at that, there's two nodes. But I have a voltage source that gives me one node equation. So I have two equations, one source gives me one node equation. So this immediately says that I have one node equation to solve. So here I go. So I'm going to write the node for V2. So if I write the node, you can see that I have two resistors. So I have R1 plus RF, V2 minus mutuals. Well, one is connected to the ground, and then you can see that 2 is connected to V out. So then I'm going to go 1 over RF minus V out equals to 0. So now that I have this node equation, what I do then is that now we apply the ideal model or the ideal conditions. So if I apply the ideal conditions, I got to look for this and I got to look for this. So once again, I look at the currents. There's no current here. There's no current around this branch. Okay, so this gives me nothing because there's no resistors there. The second thing here is that it forces these two nodes to be the same. So what we find here is that V1 is equal to Vs, which then tells me that V2 must be Vs. So now I sub this into node equation. So if I sub this into the node equation here, I come right back up here. Look what I'm going to do. I'm going to bring this to the other side. So then I get R1 plus RF. So now V2 must be the same as the source. Look at I wrote V2 is equal to V2. That is correct. And I did not write anything that's not correct on the board. It's a silly error. So now I applied this. So when I do the details of this thing, you'll see that V out is equal to 1 plus RF, R1, V source, which is exactly what we expected. I do not prefer this method. I prefer this method. Why do I prefer this method? Because it seems like I'm feeling my way through the circuit instead of sort of like writing equation after equation. Now I know node is a very nice security blanket, right? You sort of like don't think, you know, shut up and calculate, right? You don't have to think very much. God, this is such, you'll see this is way more elegant. Okay, let's do the next subject. So what I want to look at here, so I want to look at the next example here. I can't get the projector to turn on. So we start our first example now. And here's the circuit. Okay. Our job here is to figure out the out. Let me give you a little bit of time to do this. And I put the ground right here. Okay, let me give you a little bit of time. Okay, let's start looking at this technique here. Let's start off with the node. So I want to keep showing you two techniques. At some point, I'll probably run out of energy with node. But I want to make sure that if you really like the node, then you really want to practice it in class to make sure that we do that. So remember, when you apply node, you do not apply the ideal conditions until after you write the node equation. So here we go. Let's look at this guy. So clearly there's a ground here. And when I look at these node voltages here, you can see that this node right here is clearly 3 volts. So I have this node right here. And I know that this node must be the same as that. Okay, but we won't talk about that until afterwards. And then I have this node right here. So this is the out. We call this guy here V1. And then this is V2 right here. So as before here, we only had one node here. But you can see that this is an independent circuit all by itself. Right? Because one of the things that we see here is that when I start to apply node equations, I got to write this node equation and that node equation right there. Okay? So let's go look at this thing here. So the first thing I'm going to look at, note that if I look at V1, this is really just a voltage divider rule. No. I could write a node equation for it, and I'd get the exact same answer. So if I look at voltage divider rule on this guy here, you can see that V1 is really what? The voltage across the 20K. So if I write this out here, you can immediately see that V1 has to be the voltage across the 20K, and if I use VDR, it's got to be 20 over 20 plus 10 times the voltage 3 volts. Right? So you can see this is what? 30 to 3, so that's a 10. 10 into 2 gives me a 2 volts. So immediately I get that V1 or V1 is 2 volts. Now note, I can't take that 2 volts and immediately drop it into this guy right here. Yes?
So we can assume that in series because there is no current going to the...
They are in series. That's why I was able to use voltage divider.
Yeah, well, because there is no current getting into the OP.
Right, there's no current in that branch right there. So you're right, it's a separate circuit all by itself. So one cannot sub V1 equal to V2 immediately. Okay, one cannot sub V1 and V2 immediately into the circuit here. What I got to do is I got to write the node equation first. So if I write the node equation for V2, what you're going to find here is that if I look at this node, it's going to be what? It's got to be 10 plus 1 over 20, right? And that's got to give me V2 minus 1 over 20 times V out. No current sources, so it's got to be 0. So right away, what you're seeing here is that if I now solve for V out, you're going to see that, look what I'm going to do. I'm going to bring this over, then I'm going to multiply both sides by 20, which will give me 1, that would give me 20 over 10, which will give me 2, plus 20 over 20, which is 1, so I should get 2 plus 1, which is 3. So then I'm going to get V out is equal to 3 times V2, but now I apply the ideal conditions, which we already know is 2 volts, and if I plug this in, you'll see that this number then should give me 6 volts for V out. I know I'm just not kind of really thinking my way through this thing here, right? I'm just applying mathematical equations. The next method I want to look at is I want to look at simple circuit technique. Okay, so I'm going to take this circuit right here and I'm going to apply it again. So now I want to do this with simple circuit technique. So if I redraw the circuit here, what do I see here? So when I look at this circuit here, I immediately start thinking in terms of current. Like, we just already solved for this, so I'm just going to use this number. So when I look at V1, we already saw here that V1, which is the same as the voltage across the 20K, looking at this over here, we already saw that this was 2 volts. So this implies that I now immediately place this voltage in circuit. Now, I still think that this is a fairly straightforward circuit here, but over there it's super important that you do that after you write the node equation. And you'll see it'll make a difference when we get to more complicated circuits. So immediately, if I know that this is 2 volts, when I come over here, this immediately tells me that 2 must be 2 volts. So what do I do? Like we did before, follow the current. Okay? This is the ground here. So if I look at this ground, I know that the current here must be flowing. Note, as we already said before here, this current, you know what, I reversed my notation here. I called that, no I didn't it right. So this would be I2. No, I switched the notation. This should be V1 and this should be V2. It doesn't matter, right? For right now. So if the current, there's no current here, so the current has to come this way, and then the current has to continue to go in this direction. So by inspection, you can see, by looking at node V2, we immediately see that the current through the 10K must be V2 divided by 10K. So as we can see here, this will be 1/5 of a milliamp. Right? So I know that this is 2 volts, this is a 10 ohm resistor, so I know what that is. And then all I'm going to do here is that I'm going to apply Ohm's law again here. So now apply Ohm's law. And in this case here, you can see that V out, just following the current, right? Following the current. That current has to be what? V2 minus the resistor 20K times the current of the 10K resistor. Because it's the same current following through that whole branch. So then you can see here that V out is equal to V2 plus 20 times 1/5. So you can see then that this would be 2 plus 4 gives me 6 volts per V. So that's very similar to the previous one, but now we're looking at numbers here. So I want to go to the next example. This next example is a little bit more intimidating. Okay. So I'll erase this, and we'll start on the next one. Okay, so our goal here is to calculate 2 things. We want to calculate the current of the op-amp. All currents going into nodes go into the node. And then this right here represents V out. So in other words, we want to know what the current is equal to, and this voltage is equal to. Let me give you a minute to look at this thing here.
Are we assuming the current going into and out of that diamond?
No, not assuming that. Not assuming that. I mean, if you apply the ideal model immediately, then that current here has to be zero. That has to be zero. But if you apply those conditions,
So we figure out so we can reach 30K. So this year we just do a DDR and just drop across here. And drop across here.
You could do it a million times, but we're going to know that if you want to.
Not quite as good as that way, but I think
I'm going to do the same thing for you.
Roll around.
That means, and it's quite simple to that means it depends upon your actual. No, you can't, no.
hey, let's look at this circuit here. So what I want to do here is I immediately want to start looking at simple circuit techniques. So remember, you just coming out of Thevenin's theorem. Thevenin's theorem required you to have a large bag of arsenal of tricks of what to do here. So just conceptually looking at this circuit here, the current here, that tells me if I apply this here, that it means that I immediately apply ideal conditions. So that means I'm looking at this guy and this guy right there. So conceptually, when I start to look at the circuit, I can take any circuit and I can redraw it as a Thevenin circuit. Right? So that means here that I can redraw this circuit as a Thevenin. And what I mean by that here is that I'm really, the first thing that I got to do here is that I got to look at this node V1. So you know what? I'm reversing V1 and V2. So I got to stop it. So I'm going to call this guy right here V2, and then this node up here should be V1. That's the proper way to write those nodes. So if I look at this thing here, really the thing that I got to pay attention to is that I got to write this node equation. If I solve for this node equation, or excuse me, for that node, then I should be able to get V out. Because if that's the case here, then that current must be coming this way, and I'm assuming that everything attached to that line has to have zero current. And the way to see that here is that if I now take the node of these guys between V1 and V2 here, if I take this guy here, and what I want to do here is that I want to replace this with this. So when I look at this node right here, this node is V2, this node is V1. So if this is V1 and this is V2, one of the things that you could immediately see here is that this guy is connected to what? The negative branch of that op-amp here. So then that implies here that the current in this branch here is 0. So if I1, I2, I'm reversing the damn nodes again.
Yeah. Are you looking at the right side?
Yeah, the problem is that once I start, I'm gonna keep messing up. So look at this. So if the current along this branch is 0, then that means that the Thevenin resistance gives no voltage drop. Yes.
Is that top one V2 on your Thevenin phone?
Did I rewrite?
V1.
Yeah, there I go again. Whatever I write is right. Don't question it, please. Okay, so if you look at this guy here, you can see that this current along this branch here has to be 0. Right? And this current has to be that way. So now, if I look at this guy here, what this implies here is that then this node tells me then that if this node is 0 right here, right, this node right away, right here, has to be what? Has to be 0 volts, because that node and that node must be the same. So then, that means that current here, that voltage from here to here, sets V1 to be RTH. So then, this implies here that V1 has to be VTH. So our whole goal here is to solve for VTH. So here we go. So if I look at this here, so our goal shifts to solving for VTH. So let's go look at VTH. So if I look at this drop here, all I'm going to do here is that I'm going to pick one of the branches. You can see that my diamonds here are very symmetric. So if I look at this guy's a 10K, and this guy's a 30K. So all I'm going to do now is that I'm going to follow the current in these branches. So note that that branch is parallel to this branch. And so if I follow going from here to here, if I look at my drop here, my drop, since this is positive, that sets the polarity to be here, and that sets the polarity like that. So what I do know here is that because this is ground, that has to be ground, so then this must be ground, and then this guy has to be V1. So the drop across V1, so if I was to do this as a circuit here, the drop V1 must be the sum of these two drops. So the sum of drops across 10K and 30K must be V1. So if I look at that, V1 minus 0, right, from here to here must be the voltage drop across the 10K plus the voltage drop across the 30K. So now I'm going to use voltage divider rule. So I'm going to use VDR now. So if I use VDR, I know that V1 must be what? If I focus on the 10, this is a 30K, and this is a 10K. So that drop here has to be what? 10 divided by the sum. So it's got to be 10 divided by the sum times 6 volts. And then if I look at the 30, it's got to be 30K divided by 10 plus 30 times 6 volts. And what do I get here? So I get 10 over 40, which will give me 1/4. 6 over 4 should give me 3/2, so I should have 3/2. And then this guy will give me 30 over 40, which is 3/4. So that means then, is that 9/2? I think that's 9/2. So then this gives me 6 volts. Right? Oh shoot, I have a mistake. You see my mistake? Look at my line here. How am I going? Look what I hit first. I have a sign there, right? Those pesky signers. So then, this means that I'm going to get what? 9, so I get 6 over 2, which then gives me 3 volts. So I now know that's 3 volts. Let me see if I agree with me. Okay, good. That's a good thing. Okay? I agree with me. So then, if I look at this, I'm going to go right back to the circuit. So we now know this is 3 volts. So if that's 3 volts, how much current is coming here? The current here is 0. If the current is 0, then that means that the current must be doing what? Must be coming, looks like it's going down here, and then it's going up here, right? So the current's going like this here. So if this is 3 volts, I now can get the voltage across this guy. So then the 10K has a 3 volt drop, so what's the current here? Well, the current here has to be 3 divided by 10, so it's got to be 1/3 of a milliamp. So that means this current here has to be what? It's got to be 3 over 10K, which will give me 1/3 of a milliamp. So, what is the current across the 30 ohm resistor? So what's the voltage here? The voltage here is 30 divided by 3, then gives me, 30 times 1/3 should give me what? A 10 volt drop?
Hey Carlos,
Yes.
is 3 divided by 10 1/3?
Hey, stop. Okay. I wish that was, but that is not so, right? Right, so now here I go, a little bit better. So now I got the current here, so now I know that, so now if I look at the output, I think I can write still here. So now I apply Ohm's law to get V out. So if I apply Ohm's law to get V out here, I know that that's 3 volts here. So then I know that V out minus V1 must be the drop across this resistor here, which should be 3 times 10 times 3 divided by 10 times 30K. So therefore this gives me what? A 9 volt difference. Right, so that's 3, so this is 9, so therefore V out should be V1 plus 9, which then gives me 12 volts for V out. Now, what about the current I out? Well, the current I out is defined as the current coming in, but note that it's opposite of that. So then the current I out in this case is then going to be minus 3/10 of a milliamp. Okay? So I got these values here.